Just to give you already a little bit of interview of the planning of today. So we have 3 presentations, 2 by doctors. Yazeed, a recent doctor. Congratulations, by the way. So we will start with Dr. Romza Fauzan Anin. He's from University of Gajah Mada. I don't know if I pronounced that right.
Yeah.
And he will give us some insights on Indonesian karst. Then the next speaker will be Dr. Yazeed van Wyk, research manager at VRC South Africa. He will tell us a bit more about the use of artificial tracers in the vadose zone. And then there's a presentation of by myself on a research project that we are also involved in, which looks at the nitrate behavior in karst systems here in Belgium that are used for water production. So that's what we're going to talk about today. Each presentation has about 20 to 30 minutes. We have some time for some questions as well. So by 12:30 more or less, we will finish. Maybe if we go a little bit over time, it's okay. We have 2 hours in total. So it's 5 past. So I think we can start. Romza, you can share your presentation.
Okay, thank you, Sofie. I will share. Can you see my presentation?
Yeah, all good.
Okay, perfect. Okay, thank you for the chance, Sofie and Trakwa team. Thank you for having me today. I'd like to bring you closer to Indonesia. Together with our research group, Karst Research Group in Faculty of Geography, Gajah Mada University, we have been exploring how groundwater flows through this karst ecosystem, and one of the tools we use is tracer test. So today I will share a few insights from our field studies. Yeah, as we know that karst terrain or karst phenomena is represent great scientific and engineering challenges for many other expert geologists, geomorphologists, hydrologists, and many others. Yeah, this is the block diagram about karst system. Yeah, the term of karst applies to distinctive type of landscape that develop from the dissolving action of water on soluble rock, primarily limestone and marble, but also dolostone, gypsum, and halite. We move to, yeah, this is the aerial photograph from one of the karst in Java Island. In the tropical karst, we have a cockpit dolan, something like a star shape close to present. You can see this cockpit dolan, yeah, and we can move to, yeah, this is the distribution of karst in Indonesia. I take the to source one of the IAGI. IAGI is stand for Indonesian Association of Geologists, and the second one is from Ministry of Environment and Forestry. Yeah. We have 154,000 square kilometers, and karst has potential that is not only unique and distinctive, but also very rich in natural resources, both living and non-living. In Indonesia, 15% is currently under protection. Indonesia is widely recognized as a karst country. The limestone, the karst distribution in the Sumatra Island, Java Island, Borneo Island, Sulawesi, Maluku, and Papua. Okay, we jump to our research location. This is the in Sumatra Island. In Java Island, we have two study site, yeah, and in the Borneo Island, we will discuss after this. Yeah, this is the research location. In Java Island, we have 4 study sites in Gunung Sewu, Jonggrangan, Gombong, Watu Putih, Karst area. And the Borneo Island, we have 1 study site in Sangkulirang Mangkalihat Karst area. And in Sumatra, we have 1 Karst in Langkart Karst area. We move to Java Island. Yeah, this is the spatial distribution of karst in Java Island. This is Gombong Karst area in here, Jonggrangan Karst area, Gunung Sewu, one of the biggest karst area in Java, and Watu Putih Karst area in the northern part of Java. Okay, we move to, yeah, this is our publication about research in Gunung Sewu Karst area. Maybe you can read in the publication about conservation and characterization of karst water using morpho-hydrogeological method in Pindol Cave System, Gunung Sewu Karst, Java, Indonesia. And the publication is talk about one of the karst system in the Pindol Cave in the basin, Wonosari Basin, yeah. And this is the tracing flow direction of Pentong Allogenic River in the Gunung Sewu Karst area, Gunung Kidul Regency, also using artificial tracer test. Okay, we move to the next publication, and this is the publication talk about groundwater vulnerability, groundwater management based on vulnerability to contamination in the tropical karst region in the of Guntur Spring, Gunung Sewu Karst, Java Island, Indonesia. This spring, Guntur Spring, is not big spring, but also used to how to say in the people around the spring. And the next publication is about discovering water relation using hydrochemistry, isotopic data, and mass balance calculation approach to reduce the risk of impact from limestone mining. This publication also in the Gunung Sewu Karst area, but not in the Gunung Kidul Regency. Okay, we move to, and this is the publication from my supervisor, Cockpit Plus, yeah, a proposed method for rapid groundwater vulnerability driven land use zoning in tropical karst area. Yeah, this is also master thesis located in Gunung Sewu Karst area. This research talk about characterization and management of karst drainage basin based on hydrograph analysis in Gunung Sewu Karst area. We move to Jonggrangan Karst area in the west part of Gunung Sewu. This is one of the my publication about artificial tracer test for characterization and conservation of karst water in Jonggrangan Karst area in Java Island. And this is also our publication in Jonggrangan Karst. You can read this publication about karst aquifer response by time series analysis and factor affecting hydrochemistry of karst spring. Yeah, and this is also research about modeling spring flow dynamic with mudflow USG in tropical karst. This is a research of my friend when he did the master thesis. He studied in this Department of Geoscience, University of Tübingen, Germany. Okay, we move to Jongrangan Karst area. We have 3 spring, Anjani Spring, like this, Kiskendo Cave, and Model Spring. Model Spring is the biggest spring in this karst area, and also the unique spot because the used to recreation. Yeah, we use method for artificial tracer test method. I pour the uranin and thinopal and install the fluorometer FL30 and FL24 and nomogram top, and also construct the master recession curve in three monitoring sites: Anjani Cave, Kiskendo Cave, and Model Spring. Okay, the first one is the system of Anjani Cave. There are 3 injection points, Kali Cepong in the sinking stream of Kali Cepong, Kali Setro sinking stream, and also Jumbleng Sawah sinking stream. And 3 of them is connected with Anjani Cave. And from tracer test, we have 3 breakthrough curve. The 3 breakthrough curve is single peak. It means that a single conduit from injection point and observation point. The second one is Kiskendo system, Kiskendo Cave system. We injected uranin in Semar Cave, in here, with distance more or less 600 meters, and connected to Kiskendo Cave also just 1 single peak. It means that single conduit from Semar to Kiskendo. And the last one, I injected in the Nguwe Cave in here, and this is the map of Nguwe Cave. This is the plan view, and this is the extended section. And from the Nguwe Cave also connected with Model Spring. I remember when I did this tracer test, is need 2 weeks. Yeah, need 2 weeks from injection point and to Model Spring until recession. Okay, we move to Gombong Karst in the Central Java province. We have also many publication in Gombong Karst. You can see in my PowerPoint presentation about master recession curve, about diffuse flow separation, and groundwater tracing investigation to determine Kali Sirah spring catchment area, and analysis of flood recession constant of several karst spring. And the next publication is about identification of karst underground river catchment, analysis of underground river network, also using tracer test method, and cave entrance location model using binary logistic regression, also in the Gombong Karst area. In the northern part of Java Island, we also have publication this publication, this undergraduate thesis, I translated to English, study about dissolved bicarbonate variability to determine the dissolution degree at atmospheric carbon sequestration in the Rembang Karst area. Rembang is the name of region, but the name of Karst is Watu Putih. Watu means stone and Putih means white. Okay, we move to Borneo Island in the Indonesian part, Kalimantan. Yeah, in here you can see the our research area in Sangkulirang Mangkalihat Karst area. We have publication about biodiversity, geodiversity, and social aspect, of course. Okay, we move to Sumatra Island. We have one karst area in the Langkat Karst area in the North Sumatra province in here. Yeah, we have a publication about research expedition in 2020. This is the result, the distribution of cave and spring. This is you can see the map of this cave about plan view and profile. Yeah. This is the map of the cave. This is how this is the direction of slope in cave passage. We also did a tracer test to know the connectivity between this cave and in the connected to springs. We also conduct the hydrogeochemistry. This is the result of the Piper diagram. Plotting results show that 5 of the 6 springs have the chemical type of CaHCO3. This type of water show that the water flow through the limestone, so that the dissolution process occurs. Furthermore, the presence of dominant magnesium ions in the Berkali River. Yeah, this is the Berkali River is most likely due to surface flow contact with dolomite minerals and volcanic rocks. This is the injection point of uranin and connected to Gua Air. This is the observation point. Okay, one of the interesting topics is also the karst critical zone. So I will share in our research about defining karst drainage basin in Gunung Sewu Karst area, progress and future challenges in karst critical zone in the tropic. Yeah, you can see the Gunung Sewu Karst area from the west to the east consists of three provinces in the Yogyakarta province, Central Java province, and East Java province. Okay, detail of tracer test conducted by the previous investigation. I can summarize like this about date, injection point, and observation point, and travel time, and the velocity of the groundwater flow. Yeah, this is the result. Development of the Pripin Karst drainage basin. Pripin Karst is one of the biggest groundwater system in Gunung Sewu Karst area. This is, you can see the the timeline from the McDonald and Partner in 1984 and 1993, 2008, and the last one in 2013. And of course, in 2013, the catchment area in the groundwater system is defined well. Yeah, this is also our publication about tracer test in the pre-bin Karst. And from this diagram, we know that the groundwater system is not finished. For example, from Ngeranang Karst window, we don't know yet this groundwater system is flow to the spring. We don't know yet, and also the Pripyat 2 cave. Yeah. So we have a challenge to know the groundwater system in Gunung Sewu Karst area. Yeah, this is the periodization of the research in Karst drainage basin in Gunung Sewu Karst area. From this diagram, you know about the research is about cave survey, groundwater resources inventory, and then tracer test in and this is, you can see this is the author and the year of the research. And this period, the third period, is construct of Pripyat underground river, and the fourth period is research promoted by voluntary researcher. You can see so many researchers talk about groundwater system in Gunung Sewu Karst area. In the last publication is from my friends when he did master thesis. He did tracer test in Guntur Karst drainage basin, like I mentioned before in the previous slide. Yeah, this is the map of the development in the process of delineating Karst drainage basin in Gunung Sewu Karst area from the upstream area, and this is the Baron resurgence is in the downstream area. Complex groundwater system, I think. So many injection point, and just appear in the Baron resurgence in here. Yeah. We talk about challenges of karst drainage basin management in the Gunung Sewu Karst area in the context of critical zone in the tropics. Karst critical zone is a space including all its content between the top of the vegetation canopy down to deepest groundwater circulation zone. As we know that Karst area is a typical Karst critical zone as it has experiences rapid and intensive changes to compensate for the soaring human needs, especially food production. Yeah, from this map you can see the three hydrogeology subsystem. From the west is hydrogeology subsystem of Panggang, and the middle is hydrogeology Wonosari Baron, and the last one is Sadeng hydrogeology subsystem. Yeah, you can see in the middle, can see the something like graben in here. Yeah. So the groundwater system is concentrated in here in this graben. So the the groundwater system concentrated to Baron Spring, like I mentioned before, and the Panggang and Sadeng, the spring is not as big discharge like in the middle system. Okay, agricultural practices that are not environmentally friendly in several locations in the study area have caused land damage in karst critical zone, resulting karst rocky desertification. I think the problem is soil loss. Yeah, soil loss, of course, occurs differently from that one in non-karst area and progress through leakage, surface soil erosion, soil leakage, and subsurface soil loss is the main problem to based on KRD or karst rocky desertification. Okay, the main challenges in managing karst critical zone in Indonesia lie in the regulatory framework, as current policy remain at the ministerial level, yeah, while karst critical zone spans multiple sectors under different ministries. Strengthening regulation with higher legal authority is essential alongside promoting sustainable agriculture, proper waste management, and responsible limestone mining. At the same time, yeah, research must continue to define and mapping karst drainage basin as ecosystem management unit, providing the scientific basis for spatial planning and protection of water resources. In our research group, studies in karst landscape often begin with tracer tests, yeah, to identify the characteristic of groundwater system. This step provide fundamental understanding of flow connection and pathways, which then serve as the basis for future research, such as, like I mentioned before, carbonate dissolution processes, flow characterization, and hydrogeological and geochemical studies. Okay, I think that's all. Thank you very much.
Thank you so much, Romza.
Yeah.
First of all, I'm a bit surprised because I had no idea about how vast Indonesian karst was. So this is a nice surprise for me. I was completely unaware about what's happening basically outside of
Yeah.
of Europe. And I also didn't realize that there's already so many studies and tracer tests being conducted there. So that's it's a nice thing to learn that it's so well developed already. Karst research. I don't know if there's any questions from any of the participants. I don't think so. I do have some questions. And Yazeed as well, you can go ahead, Yazeed, if you have a question.
Just a quick question, Sofie. Thank you so much, Romza. That was very insightful, especially from my side as well. You know, not dealing with cost too much down here in South Africa, so it's quite interesting to see the velocities. But maybe just one other thing on the distance and the scale that you conducted the tracer tests on. Did you find that you had a much better recovery of the tracer? Or, you know, I saw there was some quick flow, but what was the recovery of the tracers in the end that you injected? Maybe you can shed a bit of light on that. Thank you.
So your question about the recovery from the water turn into green and come back in the clear water. Actually, depends on the flow characteristic, and the rainfall. Based on my experience, is one of our study site is need maybe 5 to 7 days to just for recession. But in the other research site is maybe just 1 day, and the water is not green, just clear water.
Yeah,
So
I
one
actually
day
had
you
a
get,
Yeah,
sorry.
I think it's the big discharge, so the water not how to say the come back again to the clear water, not green water.
And
but
do you
you
measure the
use
percentage?
About the percentage,
Of tracer that you can that you recovered.
recovered.
Yeah, maybe I can share the one of our research site in the Kampung Karst about recovery. Wait a minute. Stop sharing. Application. No, not this one. Yeah. Okay, I will share. Yes, can you see my screen?
Yeah.
Yeah, maybe
Yes,
in
thanks,
this.
Romza.
Yeah, this is the recovery from our groundwater system. Yeah, in the Kampung Karst area. So you can see the recovery. Yeah.
Mhm.
So
Yeah.
pretty high.
Yeah,
It's pretty high recovery.
Yeah, because I'm surprised to see like one single really nice peak in a karst area. So it's like maybe there's like things going going in the other direction, but yeah.
Yeah, especially on that distance as well. You know, you would have expected maybe I was expecting, but yeah, I was expecting maybe maybe another peak or two that can sort of identify that there's another maybe preferential flow path. But yeah, no, good. Thanks, Romza.
I've another question. You perform quite some tracer tests. Is it like, do you require permit? Is it easy to perform tracer tests? Like, is it generally well accepted to perform in Indonesia?
I think for now in our research group not conduct to tracer tests, Sofie.
But I mean, a lot of them are already performed, so I guess it's not that difficult to get permission to perform tracer tests.
Yeah. So your question about
Yeah, I was just wondering, like, do you need a permit, or do you need to request some permission somewhere from a government or like another institute to perform tracer tests?
So before we did the tracer test, we make the permission with the local people in the around the spring, and also yes, of course, from university and the government, and sometimes we also demonstrate if we did the tracer test is safe. For my experience, I practice drink drink the uranium drink the uranium, and just to show this water, if turned into green, it's safe.
Okay. That's a really effective way to
Yeah.
to show that it's safe. Okay. I don't know if there are any other questions. Otherwise, thank you, Ramza, and then Yazeed. Yeah, it's your time for your presentation.
Okay, so thank you, Sofie.
I think there's one more question, Sofie, in the chat box.
It's someone who has to leave earlier. I think that was the. No. Yeah, no, there was indeed a. So yeah, there's a question from Adrian Jones. He says, "Hi Hamza, thank you very much for the talk. I don't have much experience in dye tracing." He has a silly question, but there is no silly questions. He wants to ask whether you found that areas experiencing more soil erosion take a shorter amount of time between the tracer being put in and its recovery. Hamza? Are you still there?
Yes.
Okay.
Yeah.
So the question is, in areas where there is more soil erosion, is there a shorter amount of time between the injection and the recovery of the tracer?
Actually, until now, I don't find the area is the more soil erosion is need more time to about recovery. So that's but I think it's good question, Sophie. But for now, I didn't find the observation point that the soil erosion. So
Well, here you go. Future research question.
yeah. Thank you.
Okay, thank you. If there's no more questions, then Yazeed, feel free to present.
Thank you, Sofie. Just want to get my presentation loaded, and please tell me if you can see it. It's good.
Yeah, we can see it.
Okay, great stuff. Yes, I think it's still morning. Good morning, colleagues, and we are going to shift from the continent. You know, we Indonesian springs all the way down to the southern tip of Africa. So different geology and certainly different recovery rates as well, because we're not dealing with the karst system in this case. But yes, nonetheless, thanks for the invite, Sofie. And it's a real pleasure for me to present some of my PhD research that, as you rightfully mentioned, I've just completed. So pretty chuffed about that. And as my title reads, I'll be talking a little bit about the combined use of both environmental as well as artificial traces to sort of characterize the anthropogenically altered vadose zone and groundwater system in an open pit quarry. And this work was obviously, I have to acknowledge, I think before I go any further, my supervisor, which is Professor Matthijs Dippenaar, which has run the vadose zone, if I can call it, center at the University of Pretoria for about 10 years. So it's a pretty well-established research center. And then obviously my co-supervisors was also quite instrumental in the research, which is Professor Kai Withuser, who's from Delta H, but also an affiliated professor at the University of the Free State. And then my colleague, Dr. Yunus Bombajaswa. So I will continue from there. So I broke the talk up pretty much into a few sections. So first, I'll give you a bit of background and context of the study area, which is, as I've mentioned, an altered open pit quarry. And I will then go into the methods we use to collect the data, and then get into the data itself, and then maybe discuss the methods that we applied, and then also get some of the insights that we've gained to try and put the whole picture together in the form of some sort of conceptual model and water balance for the open pit. And then finally, I will touch on some future recommendations if time allows. So the research objectives were four, and in a nutshell, the first one was just to test how the environmental and artificial traces behave in a disturbed vadose zone as well as groundwater system, and this really helps us understand how anthropogenic activities like blasting affect solute movement. And then secondly was to quantify, the flow velocities, the pathways, and also the solute transport processes and so on. And then thirdly, we would then evaluate the performance of these analytical models against the observed tracer behavior. And lastly, was to develop this conceptual site model that pulls all the information like the geology, the hydrochemistry, the traces, to really better understand groundwater flow, particularly in a dual system. We were looking at the altered vadose zone as well as the groundwater system. So maybe just to reorientate ourselves, we are pretty much at the southern tip of Africa, for those of you who don't know. So our groundwater systems are inherently complex. We have over 80% of the country underlain by crystalline basement aquifers or fractured aquifers, and storage occurs mainly within the weathered and the fractured zones. So, and we also obviously have quite a legacy of mining in South Africa, particularly in the Wits Basin, for those of you who know, with the gold mining. And up this side, we have quite a few coal mines, and then very few open pit quarries that basically is where the research was done in the Pretoria region, where they mine the sandstone and the quartzites for aggregate and for infrastructure purposes. And what were some of the knowledge gaps that we really wanted to look at? It was to see how, when we do the blasting, what effect that has on the so-called blasting damage zones, or the BDZ, or which are often described as the sort of engineered fracture zone, because this tends to dominate transport at a very, very localized scale compared to, let's say, the regional or the natural fracture network. And we'll see that. And then obviously to investigate this, we then combine the environmental traces. So we looked at delta 18, deuterium, tritium, and then compare that with how it stacks up against your artificial traces. So again, in this instance as well, we used uranine and rhodamine WT as well. So there is the sort of critical need, for us to better conceptualize and use these analytical models to not only protect the groundwater in these altered systems, but also, I think, from a scientific perspective, is what are the sort of flow mechanisms or flow processes and that occur, in a disturbed setting like this. So when we do get to post mine closure, you know, we have something that we can give from a regulatory perspective for them to go ahead with mine closure, but bearing in mind some of the findings that would emanate from studies at this scale. So yeah, the characteristics of the study area, as you can see, it was really, well, maybe the site was firstly chosen because it was already at an advanced stage of mining. So they've closed just last year. So they were sort of lenient for us to do some research at the site because they knew whatever we would do would benefit them when it comes to eventual closure, because they obviously have to go the regulatory route to say that, you know, we've complied with whatever standards the government has set for them. So it again offered us with an opportunity to really do hydrogeological research within somewhat of a heavily regulated setting. And so again, just to orientate ourselves, it's the study site itself is located about 20 kilometers east of the Pretoria CBD. And it occupies about 84 hectares, which is relatively small if you look at the total catchment size, which is 682 square kilometers. So whatever environmental impacts we're going to have would predominantly be pretty localized. And again, because it's at an advanced stage, open cast mine, and they're extracting the quartzite and the sandstone from what we call the dust port formation. And they've been doing this for over 60 years. And that material is sort of processed on site and then used for infrastructure purposes in and around the Pretoria region. Just from a climatic perspective, we get about on average 770 millimeters per annum of rainfall, and our evaporation is quite high, 1,750 millimeters per annum. And that obviously exceeds rainfall and has a very strong influence on the recharge. They are also still actively, well, they were actively pumping. They were pumping about 3,456 cubic meters per day of groundwater, and obviously to dewater the pit. And the water that they pumped was sort of partly reused on site in the showers, in the bathrooms, and the remaining of that water was then discharged sort of just to the maybe southeast or east. If you can see the Pinars River that runs or kind of borders this side of the quarry, runs all the way out of this map, but that's a discharge point that they use when they need to discharge the remainder of the water. So yeah, so I've already mentioned that it obviously gave us an opportunity to do the research because we kind of knew that they almost at the end of their lifespan. Okay, yeah. So again, just looking at the geology, so the quarry is pretty much underlain by what we call the quartzites of the dust port formation, and these are metamorphosed sandstone, and they are also forming part of the upper Pretoria groups or the Transvaal supergroup, and it's also overlain by what we call the Silverton formation over here, and that's predominantly your siltstones and your mudstones, with hornfels sort of also present due to that contact metamorphism. And then the sequence is intruded by a number of dolerite dikes. It's these green, the green. If you can see, I'm not quite sure, I can't see it there, but it's the DB, and it cross-cuts the quarry on maybe two sides. And these soils of the Bushveld complex is quite important because they sort of infiltrated the weak planes within the quartzite that cause fracturing and has a very, very big influence on the groundwater flow at the site. So structurally, the bedding dips gently to the northeast at around 10 to 15 degrees, while these prominent subvertical joints strike northwest, and sort of the faults occur to the northwest and to the northeast of the pit, and together these lithological and structural features play a key role, as I've mentioned, in groundwater flow and solute transport in the quarry's altered vadose zone. Yeah, so maybe so these quartzites, and this is again just an aerial view of the quarry itself. So the quartzites are quite thick, so they range between about 80 to almost 100 meters. And then maybe just to give you a bit more insight into what it actually looks like at the site. Here we have the 4 observations. So at A, we have the exposed quartzite, and you can see nicely how the dolerite has intruded that quartzite along the contact with these dollarite sill. And then at B, we have some seepage. Could have put a better picture in there. That is still very low seepage. When I come to the actual conceptual setup of the tracer test, you'd see that that gap on the other side is quite big, and we have a discharge of about almost 1 liter per second. So it's pretty much spring discharging out there that we've used as our monitoring point. And again, at C, you can see that this marks the location of a bit of a slope failure that happened all the way back in 2009. Sort of again, in the rainy season, they had quite a lot of rainfall, and once the water infiltrates through the quartz sites on the contact between the diabase, they had the slip failure. And it's quite a unique feature of the quarry when you see it from up close and personal. And then D is just the quartz site displaying these extensive fracturing, which creates these preferential flow pathways for the groundwater to move. And also it gets even more fractured, particularly if you're working at a site that's actively being blasted. So yeah, if we look at the fracture characterization and the structural controls, although I'm not a structural geologist, we did include some fracture mapping and stress analysis, particularly at the bottom, because the fractures really is what controls groundwater flow at the site. So at the local scale, we see highly fractured quartzite systems that's strongly influenced again by these dollarite sills, which promotes additional fracturing. And we used 6 earthquake focal mechanisms to show the active stresses or the active stress regimes. And what we find here is that there are sort of 2 active stress regimes at the quarry site. So one is normal and the other one is strike slip faulting, meaning that the crust here is sort of being extended as well as sheared laterally. So our stress magnitude calculations was between 15 and I think about 35 megapascals. And that again suggests that the fractures here are critically stressed and also likely to remain permeable. And we went further and we mapped about 14, in the field we mapped about 20 faults, and mostly these are orientated sort of northeast, southwest, and northwest, southeast, but they dip quite steeply at about 75 to 90 degrees. And you can see that by the beach balls as well. And sort of these near vertical structures, again, acts as conduits, for groundwater recharge. They just go all the way down. And if we look at the slip and dilation tendency analysis, and this further confirms, because you can see they pretty much correlate very well. They pretty much confirm that these orientations are the most prone to reactivate under today's stress field. So I think the key message here is that the steep northwest, southeast and northeast, southwest fractures really form the dominant sort of pathways that guides groundwater flow and tracer transport in the quarry itself. And this is just a cross section from the previous slide along the side that we actually did the tracer tests, but we'll get to that now. Okay, yeah, we're just maybe dealing down into the hydrogeological setting a bit more on a much bigger scale regionally. And if you look very closely, you'll be able to see exactly where the quarry is situated. And this is just the one on the left is your aquifer yield map. And the one on the right is pretty much showing you your various aquifer classes. So regionally, the quarry sits within a fractured and intergranular aquifer system where we expected yields of anything between 0.5 and 2 liters per second, so not very strong. And the groundwater flow, again, is controlled mainly by these structural features, as I've pointed out, and the lithological context, especially between the dollarite soil and the surrounding dustboot or the weathered dustboot quartzites, which have negligible primary porosity, and again relies pretty much only on the fractures for flow and storage. And on the other side, the groundwater levels generally that we've measured and that we've got from the Department of Water and Sanitation's website, they all tend to fluctuate between 10 and 30 meters below surface. And at our site, and I'll get to that in a minute, there was this sort of natural discharge point that gave us almost 1 liter per second, and that remained stable, through both the wet as well as the dry season. So it really provided us with an opportunity to do a sort of natural, if I can call it, gradient tracer test. Okay, so Yeah, so the map shows, again, if we're looking at the groundwater and surface sampling points, I think the first thing that might jump out at you is that we were quite limited in the amount of samples that we could take outside of the quarry. And that's mainly because, you know, it's sort of privately owned land, and it's mostly equipped for livestock farming. So it's very difficult to convince the farmers, you know, to pull out all their pumps for us just to take a water sample. But we could, we got that, and we got a fairly good baseline with historical data, which I didn't display, but we managed to do that. So during the dry season, we managed to collect samples from 9 sites across the pit itself, but excluding the traces, we did that sort of separately. And as I've mentioned, these are on private landowners, especially when you got out of the mine. So, you know, it indicates that sort of limited groundwater abstraction that happens outside of the quarry. Yeah. The one restricting factor, and I think this is a bit of a challenge whenever you're working in a mining site that's actively blasting, you know, you're definitely challenged in terms of when you can sample and when you cannot. And this limited us also with the frequency of our sampling, and all the paperwork you have to go through just to get there and then get out can be quite a challenge. And maybe I should pull up the one borehole. So yeah, so this was one of the boreholes. I think it's World GO2. This is actually what they are used as a monitoring borehole at the pit itself, and we just wanted to monitor and see, you know, what's the sort of seasonal fluctuations in the bore, and we found that it fluctuates between about 5 and 27 meters, which is again consistent with the regional, as I've mentioned, fluctuations that we would expect, which is between anything between 10 and 30 meters. And again, this shows that our site-specific data aligns with the broader hydrogeological trends, if I can put it like that. But we also tend to capture these finer scale variations that's influenced by your local recharge, fractures, and quarry activities. Okay, I've got a bit of a clip. Not sure if I can play it quickly, but it just shows, you know, what the blasting looks like in real time. And maybe please tell me if you can hear that. Yeah. Hope I didn't blow you away by that. But nonetheless, so yeah, so the reason I put that up was is just to show you that, you know, when you're doing blasting at the quarry, which is obviously essential for them to do their day-to-day operations, you know, excavating that, you know, causes quite a delay. And that was done just on the bench. We were sort of on the southern part of the bench, that's towards the north. And this was happening on a monthly basis. So it was just to remove all of that material for us to get back in was certainly a challenge. But these operational and environmental effects, you know, is always going to be there when you're in an active mine. It just requires you to sort of carefully coordinate with the mine when they're blasting. Sometimes they do it impromptu. When you're there, they'll call in and say, "Look, we're about to blast," and then obviously you need to make do. But yeah, so that was certainly a challenge, but we managed to circumvent that. But again, that blasting activities is really the crux of what we wanted to understand, you know, from what is the groundwater flow and the vadose processes before, and what is it after blasting or even during blasting. Yeah, so just looking at the hydrochemical characteristics that we sort of got here. You know, we've got the sampling points, as I've mentioned. There's some a Piper diagram and also the parameter table at the bottom. And not to delve too much on this, but this is what we typically would expect. So the groundwater samples, again, mostly displays calcium, magnesium bicarbonate hydrochemical facies, which again reflects natural recharge and some carbonate weathering. And in the pit water, which is well, pit 01 and 2, should have maybe labeled it. These two, which is surface water, shows a little bit elevated sulfate, which is again typical of calcium magnesium sulfate facies. And this is likely influenced by the blasting and also rock exposure. But if we look downstream, and this is actually a historic a waste dump, but which has since been backfilled. So when we did the work there, it wasn't there, but we know historically on the maps it showed. And, you know, we kind of have a hunch that, you know, the the iron concentrations was quite high, particularly the sulfates, suggesting that this could potentially also be a contributing factor to the elevated sulfate as well as legacy contamination at the site. Okay, so looking at the sort of environmental isotopes, we did stable isotope analysis of deuterium and delta-18. I need to note this was only for one season, so it really just gives us a snapshot of recharge and evaporation dynamics at the quarry. So we obviously would need a longer term monitoring data set. So having said that, the sort of groundwater samples really cluster near the Pretoria meteoric waterline, as you can see down here. Maybe if I can just pop that arrow. And this, again, reflects sort of direct recharge from local rainfall with sort of minimal evaporation. And that's also supported by a relatively high deuterium excess value of around 11.6 per mole. And in contrast, if you look at the two surface water samples, this again just shows some enrichment with lower D excess, indicating quite significant kinetic evaporation before recharge. And this evaporation effects sort of represented by the local meteoric water line, you know, is quite steeper than the actual GMWL. Okay. Okay, looking at the D excess, so globally we know that deuterium excess is generally around 10 per mole, and that's only because the relative humidity of the free atmosphere is anything between 80 and 85%, and it really distinguishes between equilibrium and kinetic fractionation processes in water isotopes. And what we find is in our study for the groundwater samples, again, in cluster 1, it's quite depleted with, again, a high D excess, again, indicating recharge from rainfall that experienced some sort of evaporation under relatively low humidity conditions. And this possibly involved moisture recycling or extended evaporation before recharge. And not to overinterpret, but for cluster 2, this comprised surface water samples, as I've mentioned, just the two. And the interesting thing here was that we actually collected that samples after we had quite an intense one-day storm. We got around 100 millimeters of rainfall per annum. And these samples have much lower D excess, again, reflecting rapid recharge with minimal evaporation and potentially altered moisture sources and evaporative conditions that happened whilst we had the storm. Looking at the tritium and delta-18 data, again, I'm not going to delve too much on this because in essence it's again just corroborating what I said earlier. You know, we've got a mixture of sort of the groundwater samples that are depleted, low tritium content. So there's this mixture between older and a little bit more recent recharge, likely I would assume from the 1970s to the early 2000s. And then the surface water samples are, again, as you can see, pretty much enriched in delta-18 and slightly higher tritium. And this again reflects the recent rainfall and some evaporations. But one thing just to add here is that although we're having low tritium, this does not directly indicate old water. It can also result from a mixture of recent or older recharge radioactive decay, as well as dilution. So what we lacked here is a direct tritium input function, you know, for the site. So we interpreted the groundwater qualitatively rather than assigning precise ages. But if we obviously had the input function or at least a decay series or a long-term tritium data set, it would be possible to come to some sort of exact ages and maybe use carbon-14 as well. But I think overall the data confirms, at least from the environmental tracer perspective, you know, that most of the groundwater is a bit of a mixture between older and certainly more recently recharged waters, while the surface water reflects just a modern recharge isotopic signature. All right, so this is the theoretical framework. So now we're kind of shifting from the environmental traces to the artificial traces that we applied at the open pit quarry. And yeah, so it just presents a theoretical framework, you know, behind the choice of the artificial traces that we did at the quarry, and also the design to study groundwater flow and solute transport in the vadose zone. We've applied analytical modeling of the tracer breakthrough curves from the injections of fluorescein traces. As I've mentioned, we use uranine and rhodamine, and with this allowed us to obviously quantify the flow paths between our injection and our monitoring point. looked at the dispersivities and also the storage within the subsurface fractures over very, very short timescales. Here we were talking minutes to hours, and these traces were pretty much chosen for their environmental, I think, safety, the chemical stability, and also the cost effectiveness, and also obviously the high detectability that we can get with these traces. Yeah, so I think the combined approach, so we really wanted to see a combined approach to see how these weigh up against each other. And it sort of gave us a clear and conceptual understanding, I think, of the heterogeneity that one deals with when you're in a mining disturbed setting, such as an open pit quarry. And the diagram here just kind of illustrates. So look, this is broad. So these are all the traces, the applications, the methods. And the diagram sort of at the end here just shows you the various radionuclides that one can use and the associated timescales. So obviously there are, I think the point I was trying to make is to show that there are many other traces one could use, but we obviously opted for tritium. But like I said, you know, it just depends on the objectives of your study. And for this study in particular, we use the isotopes, tritium, as well as the fluorescein dyes. Okay, so if we look at the setup, so again, this is just a sort of setup of the tracer test in the pit itself. So please bear in mind, this is at a very, very localized scale. You can see that the distances here. I mean, to give you an example, that between the injection point, which is borehole 3, and you'll see there are more than one borehole, and there's quite a few. And we stuck with borehole 3 because that was the only borehole that actually gave us a breakthrough at the monitoring point, which was M1, and people tend to shy away from presenting, you know, unsuccessful tracer tests. But I put this here specifically to show that even though, you know, you don't get breakthrough, you know, from balls that are literally meters apart, it just goes to show that that also tells you something about the underlying geology and perhaps some structures that you didn't map or didn't account for, but certainly has an influence on the breakthrough that you get on a 10-meter scale. So this was from injection to monitoring is on a mere 10-meter scale, and we drilled boreholes maybe 2 meters apart. One would be bone dry, the other one would be fully saturated, and you get breakthrough from one, and from the rest, you just get absolutely nothing. So I think that's the nature of the beast when you're dealing with fractured rock and particularly blasted, impacted quarries. So yeah, so the monitoring point, as I've mentioned, is sort of at the contact. I could have put in a better resolution picture there, but it's at the contact between this dolerite sill and the quartzite, or the weathered quartzite, and that discharged at about 1 liter per second, or 0.9 liters per second, and it gave us a relatively good, a good point, or a monitoring point for us to get our traces through. And we recorded this in real time, similar to Romza, using the G-Gun FL30 fluorometer. And yeah, so that's what we used, and we got some much more lower recoveries compared to what we get in the Karst systems. You can see very clearly, not even 20%, well, 20% and 27% in the wet season, and sorry, 19% in the dry season, 27% in the wet season. And we actually needed to increase the hydraulic head in the dry season by adding extra flushes to actually get the tracer to push through. And then lastly, we've managed to model this using the multi-flow inversion of tracer breakthrough curves, which also incorporates PEST, which is obviously a calibration and parameter uncertainty analysis tool that allowed us to quantify the flow velocities, the dispersivities, the advection within the fractured vadose. Okay, so to understand groundwater flow in the fractured vadose zone, we used what's called MFIT, and this is the multi-flow inversion of tracer breakthrough curves, version 1.0, and this really simulates complex tracer behavior. It is an open source tool for fitting tracer breakthrough curves. It was developed by Professor Jacques Baudin, who I've also published a recent paper on this. And it's probably, for me personally, probably one of the better ones one can use that is freely available. I'm not saying it's the best, but certainly better than the rest when it comes to freely available and open sourced software. So it allowed us to test these 4 sort of, you know, analytical solutions. The first one was the multi-dispersion model with an instantaneous injection. And then we moved on to the MDM, which is again also multi-dispersion model for exponential decay in this instance. And then we looked at the multi-dual porosity model, or the single fissure dispersion model, and then also the multi-dual porosity two-regional non-equilibrium model for dual domain transport. So it accounts for both mobile as well as immobile zones. So the concept here is that, you know, we employ the N-channel solution. So if you look at the two that we predominantly applied is the MDMI, and you can see it's got a fewer fitting parameters, but it uses more channels to simulate the dead end or the immobile zones. And if you look at the MDP2RNE, it obviously captures the immobile or stagnant zones, so that so that exchange between your fracture and your stagnant zones very well. But we have much more fitting parameters, which makes it slightly more complicated. And so both the MDMI as well as the MDP2RNE models were particularly notable because they tended to integrate the multi-flow as well as the dual porosity concepts at the channel scale. So while the aquifer heterogeneity is represented more by these independent one-dimensional channels that we use for the MDMI solution. And then again, MFIT is fitted with PEST, which obviously enabled us with automatic calibration and a bit more a better uncertainty when we looked at our values. And this is just a sort of conceptual understanding of what happens within your fracture. We discounted diffusion, even though the single fissure diffusion model, you know, was also run. We excluded it because we had such quick breakthroughs, as I've mentioned, from minutes to hours, and we know diffusion is normally over a much longer time period. And if you don't have reliable effective diffusion coefficients, you know, we still felt that it would make sense to stick with the two-regional non-equilibrium model. So we discounted diffusion, but we did look at the immobile and mobile zones, which was pretty evident in the breakthrough curves as well. Okay, so we've got sort of the wet season and the dry season, and this is what the breakthrough curves look like. You can see we have in the wet season, we had mean travel times of about 45 minutes and a mean velocity of about 2 × 10⁻³ meters per second with a very low recovery of 27%. These multiple peaks, yes, they certainly do indicate to more preferential flow paths that's sort of integrated within the fracture network. But in contrast, if you look at the dry season, we have sort of exhibited quite a delayed and attenuated peaks with much lower recovery, 19%, and but much quicker arrival times, so about 11.7 minutes, and velocities of about an order of magnitude higher, which is 9 × 10⁻³ meters per second. And this just suggests that there's reduced connectivity and more of a divergent flow, likely caused by the lower fracture saturation and possible changes in fracture apertures, potentially also amplified by the recent blasting. But perhaps maybe just to get back to the dry season, it's important to note that we actually we added 85 liters of flush fluid, you know, to sort of initiate the tracer movement. So we temporarily raised the head in BH3 by about 1 meter, and this was really this partially, to an extent, reconnected those dry fractures. So the higher measured velocities that you're going to see on these peaks are partly an artifact of the added head, you know, so not necessarily the fractures, but the added head. But this could also indicate that under dry conditions, only a few fractures carry flow, acting as high velocity conduits. So these seasonal differences highlight the dynamic nature of groundwater flow at the site. But we need to bear in mind that the latter two peaks, we just refer to them as flush peaks, and they were not used in the modeling at all. We just focused on the first peak because that was pretty much just flush peaks, and it wouldn't have had any value if we were to model those. Okay, so looking at the wet season breakthrough curves, as I've mentioned, the reasons for applying the MDMI and the MDP2RNE models, the first thing that jumps out, you'll see that there are much more channels for the MDMI And you might look at the breakthrough curve and see, well, hang on, I count maybe 1, that could be 2, 3 peaks. Why do I have 12 channels? And the way we explain that is that the MDMI, because it's a simpler representation, it's a multi-dispersion model. So what it tries and do is to simulate fast and slow flow, or to account for stagnant zones, because inherently the model doesn't have stagnant or immobile zones built in. So what the MDMI analytical solution does, it actually adds more flow channels, you know. So you have a fast and then you'll have a slow, and that in essence tries to simulate these stagnant zones. Whereas obviously, and if you look down, you quickly see that the MDP2RNE has much fewer channels, because it actually accounts for mobile and immobile exchanges. And that was something that was that just to bear in mind, that so when you look at the results, that you sort of get that concept. And just with the PEST, if you look at the PHI versus the number of channels, typically what you'd find is that this would decrease with the more number of channels that you add, and that's exactly what you get. And similarly with the MDP2RNE, so this decreases, as I've mentioned, with more channels one adds, but at a certain point, adding extra channels, doesn't really improve the fit much. So then you run into issues of overfitting, but it does help us identify a sort of parsimonious model that's enough channels to capture the flow behavior without overcomplicating or without overfitting the model. And these results really help us sort of quantify fracture connectivity in ultimately to support the conceptual understanding of what's happening at the site. And there's a link by the paper by Prof. Bowden that sort of goes into a little bit more detail in terms of how we do this. For the dry season, you can see clearly. So if I can just quickly go back. Okay, that's maybe just too far back. In any case, you saw on the dry season there were 3 peaks, and this is pretty much just the first peak for reasons I've just explained that we've modeled. And again, we applied both the MDMI and MDP2RNE, and you can see we get 4 channels for both. So they both equally fit the data pretty well. You can look at the PHI values and the number of channels as well. Noting that we added the 85 liters flush fluid, so we didn't account for the other peaks. We just wanted to get what's the real sort of state in the dry conditions at the site. So the breakthrough curves were obviously a bit broader and more attenuated with lower peaks and long tails, and this reflects a much stronger dispersion, and the influence of immobile or dead end zones are pretty much captured. So the transit times, as I've mentioned, was surprisingly a little bit quicker. So in the wet season, as opposed to the wet season, that was between 6 and 11 minutes, we already had full breakthrough. And this was concentrated along, these 4 channels. And the velocity was an order of magnitude higher as well. And the dispersivity was also quite high. If you look at the dispersivities, it was 0.018 to about 0.75 meters, indicating more tortuous spread out flow paths. So yeah, so that's what we got for the dry seasons modeling component. There was something else that I wanted to quickly mention, and okay, but I'll get back to that. Okay, so I think that the sort of key takeaway here is that we in the dry season we had faster velocity, greater dispersivity, which is a bit counterintuitive. In the wet season we had lower velocities and slightly lower dispersivities as well. And yeah, maybe I should stop here and just quickly ask that. Again, you can clearly see, so I see 1 peak, 2, and maybe 3 peaks, and then they have some tailing. And you might ask, well, you know what, if I was just looking at this, I see 1 or 2 peaks, where's the other 2 coming from? So what this means is that when you do a superposition, let's for argument's sake say you've got 2 channels and they are flowing. One's flowing at a slightly different velocity, and the other one is flowing at a slightly maybe higher or lower velocity. They actually come up as 1 peak, but these 1 peak could actually be more than 1 flow path. you know, it's just that the model captures it at 1, but if you look at the flow within that specific channel, you see that it differs quite drastically. So sometimes, you know, when you look at it from first glance, you might see 1 or 2 peaks, but in reality, it could be more than 1 peak, particularly if that flow paths are flowing at exactly the same velocity. They tend to mask each other, and so you can't just see it visually. You need to actually do some model and calibration to get that. So yeah, so maybe just in essence to sort of round it off, to compare, in the wet season, we've already mentioned there was slow and relatively uniform flow with a mean velocity of 1.6 times 10 to the minus 3. We had a whole order of magnitude higher in the dry season. Similarly with our Vmax, you can see the changes in transit times, much longer in the wet season, very short in the dry season, high per clay numbers in the wet season. And the trace recoveries are all listed there for you to have a look at as well. We then had to move on to the conceptual site model, and this pretty much just really tried to integrate everything at a very, very localized scale. You know, so we tried to integrate the geology, the fracture characterization, the tracer transport, the environmental isotopes to describe groundwater flow at the site. And it's abundantly clear that the system behaves as a dual porosity aquifer, where we have fast flowing fluid in the fractures and much slower flow in the stagnant zones, and that the preferential flow pathways really concentrate along this dolerite and quartzite contacts. And you can see that running all the way through the quarry if I was to dissect it. And there was certainly some challenges as well. You know, we, for argument's sake, had this BDZ, and we just didn't know whether it was acting facilitating flow or whether it was a barrier, because if you had 7 boreholes and only 1 of them gave you breakthrough, it probably means that there are some underlying structures that's not contributing to flow as quickly as the 1 borehole. But maybe to add that when we came back, so when we did the tracer injection on 1 day and we came back, I think it was 2 weeks later, the whole pit was green. So that does mean that, you know, eventually the tracer will come out. It probably just didn't come out enough during the time period that you were sampling for. So that's also a key one to look at. And then we got some T and K values. So this was pretty much from historical pumping test data that we analyzed using Actisolve, and we've got hydraulic conductivity estimates. So the bore that we used was not in the pit itself. It was just to the north of the pit that they used, that was sort of used as a monitoring borehole. So it might not necessarily be representative of the conditions within the quarry, but we've got transmissivities between 2.5 and 4 square meters a day, which is useful for regional context, but it differs quite markedly if you look at the tracer velocities that can be hundreds to thousands of meters per day. So I think the scale as well as the heterogeneity, you know, distinguishes that pretty well. But nonetheless, we managed to put some numbers to the regional groundwater hydraulics. I'm almost there, I promise. So looking at the pit lake water balance and maybe just some 3D conceptualization. So yeah, so because it's it pretty much illustrates for us that we went the steady state water balance for the quarry. So the general water balance is, as you know, change in storage equals your inflows minus your outflows. And at steady state, you know, the inflows we would assume and the outflows are in equilibrium. So the change in storage would be 0. But for this pit lake, your inflows from rainfall and groundwater seepage was around 75 megaliters per annum, and then the outputs, which is your evaporation and the limited pumping that I've mentioned earlier, it's about 106 megaliters. So this results, it gives us a sort of net deficit of 31 megs per year. And on paper, this would suggest that, hang on, your pit lake should be shrinking, but when we did the field observations, it shows that the lake or the lake volume remains relatively stable, which indicates to us that there are additional surface runoff, particularly during the rainfall events, that is contributing to inflows, but was not fully accounted for in the initial calculation. So also based on the contributing catchment, that is very important. The contributing catchment was about 450,000 square meters, and the pit lake only 390,000. So the estimated mean annual runoff of 79, I think it's there, millimeters is plausible, and likely explains the apparent deficit of 31 megs. So in essence, the pit lake pretty much functions as a terminal sink with no measurable outflow to the surrounding surface water or groundwater, but seasonal fluctuations in volume are primarily driven by rainfall evaporation imbalances. And the last two is just a 3D geological block model that kind of shows the structural controls on the faults, the dolerite intrusions, as well as the quartzite bedding. So we took that from the initial fracture characterization and managed to come up with some sort of 3D conceptualization of what we have at the site and just how dominant or how prominent this diabase sill is in navigating flow at such a localized scale. So yeah, just some of the key research outputs for that we've sort of done over the last 3 years. As I've mentioned, there are some DRI links for those of you who want to have a deeper look in the work that we've carried out. And they cover the methodology, the trace and isotope analysis in a lot more detail, and also gives you a bit more insights into groundwater flow and solute transport in this altered vadose zone setting. So by all means, I'm sure you'll share this presentation as well, Sofie. Yeah, so maybe just to get to the end of things, the future possibilities and what are the limitations. I think in a sense that the study demonstrated the value of combining environmental as well as artificial traces with isotopes to unravel sort of some of the complexities at the site, which I think we kind of got there. Maybe another limitation I would say would be that this was just a single season of isotopes sampling, so it really provides us only with a partial picture of what's happening from an environmental tracer perspective. So we would need multiple season monitoring that would capture the recharge variability with a little bit more confidence. And if we integrate the long-term tracer testing with the numerical modeling, this can further enhance our ability to predict the system's behavior and inform. Ultimately, what we set out to do was how do we come up with the research that we can provide to the mine for post-closure groundwater remediation strategy, because they have since closed. And a lot of what we've done here helped them actually satisfy from a regulatory perspective to actually close the mine and use it for whatever purposes that they are planning to use it. So yeah, so nonetheless, I think the tracer-based framework is adaptable. You can adapt it, and it really offers, I think, a practical approach for sustainable groundwater management in post-mining and other complex fractured rock aquifers across the country. But we need to bear in mind that each fractured system is number one, it's unique, and site-specific geological disturbances may, to some extent, limit how directly one can transfer, or the transferability of the results to another site. So to wrap up, we demonstrated that groundwater flow and solute transport at the quarry is predominantly controlled by these fracture networks, and with quarry blasting, we have active blasting. This further modifies these pathways. Having one bore contributing to the tracer, it just means that the other boreholes potentially on the benches above could well have been collapsed due to ongoing blasting, and that's something you need to account for, that your flow regime can change in a split second, typically due to this blasting. And then the tracer test just confirmed that there is local recharge and seasonal variabilities, and the preferential flow paths are pretty much has a massive role to play in getting your tracer through to the system. So this work, I think, goes one step further, and it really highlights that the importance of not just using a single tracer, but using multiple tracers, combined with stable isotopes and even radioactive isotopes to gain a better, deeper understanding of the system that we're dealing with. And then, we can then go into the analytical modeling, which we did. And we also ended up doing the numerical modeling, which we pretty much close to completing. That's pretty much how far we got. And thank you very much. And this is just the team. It's quite a large team. But yeah, it wouldn't be complete if I thanked all of them, especially the supervisors, my colleagues, the field assistants, the examiners, and even the anonymous reviewers who support and feedback made this research possible. So thank you very much. Apologies, I might have gone way over time. So if you have any questions, thank you.
Are there any questions? I don't think so. I do have a question though. Did you have tracer tests? You did tracer tests in dry and a wet season?
I beg
Were
your
they,
pardon, sorry.
you did a tracer test in the dry and the wet season? And were there blasts in between those different tracer tests? So
Absolutely.
how did you distinguish between the effects of the seasonal variation and the effects of blasting, which might have completely changed
Yeah,
the
absolutely. Yeah,
layout?
no, yeah. So what we did was and actually that's my colleague right here. Maybe I should bring her into the picture. She's the rock engineer, and what we did was to distinguish between that. Maybe I should have brought her up. Is that I was looking at from a hydrogeological perspective, and she was doing the actual rock characterization, and we used thermography. So infrared thermography mapping. So we basically use a thermospectral camera. We saturate the bench with below freezing water, and we try and do this in the summertime. So it's sorry, yeah. So it was during the summer, so it gets pretty hot. So about 40 degrees, and we went way below zero with the ice and the truck that we pump water into the rock face. So just prior to blasting, we already had the results, so we knew that okay, the groundwater is flowing northwest southeast. So that's the general trend. And then we wanted to see, well, how many fractures can we pick up that's either opened or closed, and to see what the flow paths does. And she's done, and her paper will come out soon. We on at the same site. And when we looked at the infrared thermography, you could actually quite clearly see, how when we saturate the whole bench, you could actually see. Sorry, so she did this also while I was doing my research. So we had a baseline of what it looked like before and after, and it was completely different. And that's where the blasting damage zone comes in. So when you blast, it actually the area that you're working at certainly gets affected, because we were blasting only a couple of 100 meters away. In that, some of the fracture apertures actually closed down and diverted flow, away from where we would expected it to be. So it eventually came out, but this was all captured on the infrared thermography. And that paper from Ampoma Oy will come out soon. And we are pretty much active on LinkedIn, Sofie. So I would post the link to that paper. But yeah, certainly there was intermittent blasting, but we managed to capture it with the infrared thermography mapping. Yeah.
Okay, yeah, that's quite an
Yeah.
impressive big research that has been done. There's a question from Lucatas. It seems like in the model you understand the geology and presence of preferential flow paths quite well. What would you do if you did not have a very good understanding of the orientation and number of preferential flow paths?
Yeah. Okay. Thanks. Is it Luca?
Yeah,
Yeah.
Luca.
Okay. Yeah, Lucas. So thank you very much. Yeah, that's a very good question. I mean, you have to understand that I think with any research, and particularly at this site, it was we didn't have anything to work from, so we kind of went in there blindly. So the first thing that we typically would do as hydrogeologists is to do what we call a hydrocensus. So we look at what information is available, what studies have been done in and around the area of interest. So if we look at the mine didn't have much in terms of data, but what they did have some very good environmental impact assessment studies that were done by consultants. So that at least gave us a sense of what was going on, but not clearly at the level that we wanted to look at, and that is obviously, as you rightfully mentioned, the preferential flow pathways. Where are they situated? How are they orientated? So we did quite a number of mapping, because we really didn't have a very good understanding of what the fracture system was, and that was very evident. If I can show you. Sorry, Sofie, I'm just going to quickly go back, just to show you that we yeah. So, oopsie, maybe I'm going too far or too. No, I'm too far. I want to show you where the actual setup was. Yeah. So yeah, here we go. So if you look at the setup, Luca, you can see that that's BH3. So that's the only borehole, and this is at a very, very localized scale. Okay, this is a couple of meters. And from our initial mapping, you know, we understood that northwest, southeast, northeast, southwest, if you look at the faulting, if you look at the fracturing, the orientation that we mapped, that we would expect groundwater to flow. And that's, you can see it channels exactly the orientation of our main regional groundwater system. So we, in our minds, we were like, okay, this is exactly where we would have groundwater flow. And to make it more interesting is that if you look at the discharge point here, M1, this is directly below. This is directly below the bench. So again, it just confirmed that, you know, this should be, you know, the orientation, because we're having natural discharge of almost 1 liter per second, which is quite substantial. But you can see that we then drilled along the bench. We drilled 4 boreholes, I'd say 5, in some instances 10 meters, 20 meters apart. We went to the bench above. So maybe I should have mentioned the bench heights are about 10 meters on average. So that was, so these boreholes, you can see these at the lower bench, that's at the higher bench, and then at another bench. Okay, so about 10 meters, 10 meters, 10 meters. And we had absolutely no breakthrough. So before we even did the using artificial traces, we also did a salt ball dilution, you know, so as a precursor before you do your actual tracer test. You don't want to waste any of your resources. So we just put in some salt, and even with the salt, we couldn't get any breakthrough. And that's obviously could be due to density effects, or just, you know, again, that blasting damage zone, or some structures that we didn't map. We did later on, and I have to add this, we did later on get the Council for Geoscience to come out and do some geophysics for us, and we managed to pick up some of these hidden fractures. But to answer your question, if you don't have a good understanding of your orientation or your preferential flow paths, you need to do a couple of things. And I think the first thing is you would have to map the fractures, so what you see on the surface. And if you have more resources, you can even go downhole. You can use video camera logging, so you can actually visually characterize the fractures in your system. And because these were boreholes that we drilled, we also logged the borehole. So we looked at the lithology and where the fractures are. So I didn't put all of that information, but you'll find that in the publication. So we logged all these boreholes. So we kind of had a very good understanding from borehole 1 to 7 where these fracture zones are. And you can then sort of, if you put it in a 3D model, you can easily see how they connect and where they don't connect and where they might be dead ends. So yeah, so I think in South Africa, and I've mentioned this at the beginning of the talk, we have a very, very complex aquifer systems. And I think this complexity shows that on a 5 meter distance, you can drill a bore that's completely saturated, and 5 meters away from you, there's absolutely no water at the same depth, targeting the same formation, and you just don't get any breakthrough. But that's tracer test for you, right? You don't always get it right, but every I think every result that didn't go our way definitely helped us. So that's why I say a negative result shouldn't always be looked at in a bad way. It actually helps you inform your conceptual understanding of the system a lot better. So it forces you to go back and relook at, okay, am I missing something, or what else can we use to better get a sense of the fracture orientations at a very, very localized scale, colleagues. This is not at a kilometer scale, like we've seen in the previous presentation. So you might think it's a lot more easier at such a small scale, but it can be quite difficult. Even with the numerical modeling that we did, it was exceptionally tough. But yeah, we got there in the end. So thanks. I hope that answers your question.
Okay, well, thank you very much, Yazeed. Very interesting. I've seen the research passing by quite often on LinkedIn, and now I finally have an in-depth presentation of it. So thank you very much.
So much. You're most welcome. I'll stop sharing at this point. Yeah.
Okay, we have about 20 more minutes. I will try to keep it as short as possible. There is a longer version of the presentation that I am about to give already on our YouTube channel, because I gave like a lunchtime webinar once that lasted an hour. So if you want to have the longer version, be sure to have a quick look at our YouTube channel. But now I will give like just a shorter version of our Epukarst project. If I can open it, here we go. I hope everybody can see the presentation. I don't hear anything, so I guess it's all good. Okay,
It's
so
fine.
thank you, Yazeed. So Epukarst, it's a research project that Kakwa is involved in, of course, with other institutions and companies as well. And it's to have an idea, a better understanding of how nitrate behaves in karst systems in Wallonia, which is in the south of Belgium. Just to give a quick context, so here we have Belgium. We are bordered by Germany and France, for the people who are not from Europe. Wallonia is this southern portion. It's very important for drinking water. Most of our drinking water comes from groundwater. And from this groundwater, a lot of it comes from karstified limestone aquifers. We have a lot of agriculture, so unfortunately nitrate pollution is a real threat. There's also quite high population density, which also provides nitrate pollutions. But it's not very well known how this nitrate moves or is maybe stored within karst aquifers, which is quite a big gap in our knowledge, knowing that a large portion of this karst aquifers provide our drinking water. So what Epukarst tries to do is try to identify some trends on where nitrate is stored, how does it move through the system, how does it move through different compartments of a karst system. So you have swallow holes, you have the unsaturated zone, you have underground rivers, you have springs, and Epukarst tries to uncover what is going on in these karst systems. So this is the southern portion of Belgium. This is Wallonia. All the dots indicate the nitrate monitoring points. Here you have the scale. So when it goes on the red, above the red, it's more than 50 microgram per liter, which according to the European Drinking Water Directive is too high to be used as a drinking water source. So some points are already above this this maximum. You have some orange points and yellow points as well, which are getting closer to this maximum value, which means that if they go above 50 microgram per liter, the drinking water producers are no longer allowed this particular zone or catchment as their production site. So we had some producers that were very eager to participate in this project. The project exists in two phases. So there's a first phase that is now finished and a second phase that is currently ongoing. The first phase is really an experimental approach. It was actually a citizen science project, which is really nice. And the first phase was really used to test methodologies, to test instruments, like how to set up certain instruments, which ones were better, which methodologies to best use to monitor nitrates in karst systems. The first phase was not done in actual catchment sites that are used by drinking water producers. These 5 karst systems that were chosen were actually systems that were already pretty well known. So they were already characterized. Tracer tests have been done in the past in these karst systems. They were mapped pretty well. So these are 5 quite well-known karst systems in the south of Belgium. And to each karst system, there was a local caving team designated to this area that did all the monitoring and the measurements in their karst, in their cave system. So of course, we tested several instruments. We measured and monitored different parameters. Some are quite like general, like temperature, pH, dissolved oxygen, etc. And then of course also nitrates. All the health hand instruments were also calibrated and compared with laboratory tests. Of course, our five caving teams were trained on how to use these monitoring tools. They were trained on how to sample, how to analyze the data, and also how to report. They sampled every 2 months for a period of 3 years. They all kept very well to the schedule, and they finished the 3-year monitoring period, which was really nice. And on top of the training of the local cavers, there was also some general education of the citizens around these cave systems to make them aware of the problems related to nitrates in groundwater and of course also drinking water. So this is the result of the first phase. We had 110 sampling days with over 10,000 data collected by these caving teams. They collected data in the different karst compartments. So they collect data in the sinkholes or the swallow holes, in the non-saturated zones via drip systems. So when you have stalactites, you can have like water dripping from them, and they collected this water dripping from the stalactites or in little ponds that form under the stalactites as a, let's say, a proxy of this non-saturated zone. Of course, you have the saturated zone with the phreatic layer. In karst systems, you can have some underground rivers, and they also monitored the spring at the end. This is the general results of these 5 cave systems in the first phase. And some things that I just want to show that are quite surprising, at least it was not exactly what we expected. If you see, for example, in most systems for FOS, we're going to ignore, I will explain you later, the results are very different there. But usually the nitrate content of the swallow holes are lower than what we see in the other karst compartments, which to us was a bit surprising because when we think about swallow holes, we always think, oh, these are kind of highways for pollutants, rainwater or runoff can flow into swallow holes very quickly. You might have a high concentration, but this is actually not what we saw in reality. Like the nitrate contents on average were lower than what we see in the other compartments, for example, in the underground karst rivers, in the final karst springs, even in the surface water downstream. On the other hand, we see that the nitrate content in the unsaturated zone was on average higher and also with a lot higher variability. There is definitely a seasonal variability in the nitrate content. And we also see that the nitrate contents in the underground river and the springs were kind of intermediate between these unsaturated zone values and the values that we found for nitrate in the swallow holes. Again, FOS is kind of a unusual system because it's not really a swallow hole. It's basically a river system that goes underneath and then flows out back on the other side. So this is not really a swallow hole, it's a river. And there's also some local communities living nearby that that reject the wastewater directly. So you have a big input of wastewater actually, which creates a very high nitrate content. So FOS is a bit of an exceptional karst system that we don't really consider here. So what's the final lesson of the first phase? We saw that the unsaturated zone actually contribute quite a lot to the nitrate content compared to the swallow holes, which had lower nitrate contents. There were not really seasonal trends in the swallow holes, but on the other hand, for the unsaturated zones, which were measured again via the strip system, we really saw a seasonal variation. And then the Karst River and the spring had intermediate values between the unsaturated zone and the swallow holes. And also we saw the box plots were a lot smaller, so the nitrate content was actually quite stable throughout the year. So this is that were the results of the first phase, which of course then we used as some very important information on how to set up our monitoring for the second phase, which only started last year. We also were able to select some interesting monitoring tools based on the experience of our caving teams. So this time we did choose 5 karst systems that were used by drinking water producers. They usually measure nitrate content 4 to 12 times a year manually, and then they send it to the lab. 4 to 12 times, it depends on the size of the drinking water producers. So smaller producers have to do minimum 4 measurements a year. Bigger producers have to monitor every month. But even then, knowing that there is a seasonal variation, 12 times a year is not that much. So what did we want to do with this second phase is really to identify much more closely the nitrogen variability within these karst systems, and also improve just the general hydrogeological knowledge of the karst catchments, which are currently not very well known by the drinking water producers. And of course, with the general objective is to provide these drinking water producers on how to better manage their resource and to also better manage the nitrogen pollution threat. So this looks a bit complicated, but let's go through it together. So what is currently known by the water producers is basically how much nitrate is, what the nitrate content is at the spring. So where they capture, or at the catchment site. So where they capture the drinking water, there is what they measure, where they measure the nitrate concentrations 4 to 12 times a year. But everything else, what is going on here in the non-saturated zone, the saturated zone, they have no idea what is happening there. If for some sites the nitrate content is actually getting quite high, so close to this limit of 50 microgram per liter, then you have Protecto, here it is, Protecto put in place. Protecto is some program that is put in place by the governmental body, and Protecto will measure entering nitrates, so entering nitrate fluxes. So they measure the first 30 to 90 centimeters of the soil, and they measure nitrate content within this soil. And then based on this data, they give recommendations. They don't have the power to actually put limitations. They give recommendations to the local actors, such as farmers, maybe local communities, to adapt their use of nitrate. But this is only when the water producers notice a very high concentration of nitrates, then Protecto is put in place. So of course we want to go in much more detail to know what is actually happening within here. Like, is it stored? What is the transfer? We only basically know entrance if there's a high nitrate concentration, and then exit. But what's happening here? This is basically the research question of Epukarst. So these are the other sites, 5 new sites that were chosen for the drinking water producers. 6 is a reference sites that we kept from the first phase. This is just some historical data of the nitrates done by the drinking water producers. Some sites are quite stable, other sites have very variable nitrate concentrations. You can also see that in the beginning they measured quite often, and you see a lot of peaks, a lot of lower values as well, a lot of seasonal variation, and then they kind of decided to take less measurements a year, and then suddenly all the peaks and the low points are gone, but we see an increasing trend in the nitrate content. So Neuffontaine is definitely one of these sites that is under threat. They are reaching this value of 50 microgram per liter nitrate content. If it goes over, they can no longer use this site as a drinking water production site. So they were very happy to participate in this Epukarst project because they, of course, hope to get some recommendations on how to change this this trend. This is some of the equipment that we put in place. We have a EXO3 nitrate probe to monitor in situ every hour nitrate content, which is of course on a very, very different scale of the current 1 to 4 times a year monitoring of nitrate. We have electric conductivity, we have meteorological data. Of course, we still have the routine sampling, water sampling by the water producers. We ourselves also did manual sampling to compare the exo nitrate probe with lab values as well to be able to calibrate. We did pumping tests. We measured the water level regularly. We did some flow measurements. So for each site, we did a very in-depth hydrogeological analysis, or at least that's planned because we still have some years to go and we didn't do every site yet. Here's some ideas, some nice pictures. Here you see how we sample the drip systems. So this is to give this works as a proxy for the nitrate concentration in the vadose, in the non-saturated zone. And this, I will not go through the graphs of each site, but this is, for example, the Neuffontaine site, which is the site that is getting closer to this limit of 50 microgram per liter of nitrate. The blue bars indicate a rainwater event, and the purple or the pink bars are I don't know how to say it in English, eau utile, which is the water that is able to infiltrate to the phreatic layer, to the groundwater system after rain events. So the excess water, I think, is the English word. The green line is the monitoring of nitrate with the EXO instrument, and then the green dots is our manual sampling. As you can see at the start of the project, there's quite a difference between the values of the manual sampling that we then analyzed in the lab, and then the in situ monitoring probe. This is due to calibration. We really had to learn for each site and for each position how to correctly install and then also how to correctly calibrate the instrument. It's a bit tricky to work with this type of nitrate probes, but you can see that over time we got better at it, and the actual values of the manual samples are getting closer to the values given with the automatic monitoring probe. So this is something that happened for each site. We really had to see how to best install the instruments, how to best calibrate the instruments as well. It's a learning it's really a learning process. So it's good to keep in mind if you ever use this type of instruments, that the first values that you get will not necessarily be the actual values. It's always very good to keep manual monitoring as well, to calibrate very, very good, and to learn how to best set up. This is another site. It's more stable. You have two rows here for because they actually put on and put off the pumps of the drinking water producers. So each time that they put on or put off, you have a little jump in the nitrogen values. And this is another spring or another borehole, but in the same Spontin catchment site. Here we see something interesting, like we have this excess water in pink again, and we see that whenever there is excess water, we have a sharp drop in nitrogen content. This is because of dilution. This is a dilution effect. But something else which is very interesting to see, so there's a big rain event, you have a dilution effect, nitrogen content drops, then it goes up again, another rain event, it drops, it goes up again, and so forth. But there is a general trend, upward trend. Of course, this is all still hypothesis, but we think this is because whenever the groundwater level rises, it actually goes and collects some nitrogen that is in the vadose zone. So the groundwater level rises, it goes and collects nitrogen from the higher layers, and then it drops again. The water drops again and has a higher nitrogen content because of it. And so this basically means that in this case, the vadose zone would definitely be a storage site for nitrogen, which is not always the case. We have other areas where we don't see this upward trend. We do see this dilution effect, but not necessarily an increase in the nitrogen. So there's the rise in groundwater level doesn't necessarily mean that it goes and captures more nitrogen from the unsaturated zone. This is another site, again, quite stable. The pink and the orange are the nitrogen contents, quite stable. Sometimes you have a little shift. This is the moment that we take out the instrument to clean it, to calibrate it. These are just water levels, the peaks. Again, another site, quite stable. I will not go into detail. This is the big drops are because of calibration, and then reinstalling the instrument maybe slightly different than it was before. So you have these shifts once in a while. And again, quite stable. Sometimes we have lost some data, unfortunately. This is all of them together, but I will skip this for now. This is the site of the first phase. So this is not a drinking water producer. It's quite. No. This is a drinking water catchment site, but this is the one that is getting quite close to this 50 microgram per liter. So they really want to know how they can avoid this. The purple one, however, is the site from the first phase, which is just a natural case system that is not used for drinking water producers. And there, of course, you see a lot of variation in the nitrogen content. And the other sites, luckily, are remaining a little bit more stable, which is good, better news for the drinking water producers. We did, on top of that, of course, we didn't do it for all sites yet, but we will do geophysical investigations. We will do electrical resistivity tomography. I don't know, ERT. I don't know what exactly it stands for. We will also measure the leachable nitrogen. So we will take soil samples. We will try to go deeper than what the Protecto program is doing. So they go up to 90 centimeters. What we will do is go as deep as possible. So sometimes it's up to 4 meters. This is as far as deep as we can go with manual sampling. And we will, of course, also do a lot of tracer tests to really characterize the karst systems a lot better. So this is the soil sampling to analyze the leachable, potential leachable nitrogen. This is what Protecto, the program, is doing, up to 90 centimeters. What is going to be below that is currently unknown. So we will add those data as well. We will do fluorescent tracer testing, so we will inject dyes in sinkholes, and then analyze them with a whole monitoring system that we put in place. We don't use the Albilia G-gun, we use our own instruments. We have compact fluorometers, so we can really put a whole network to characterize as detailed as possible, to really have a good idea how this karst system reacts through rainwater events, to have a better idea how the nitrogen potentially moves through these systems. So this is one that we did last summer. So we injected here. This is one of the sampling sites where we installed a fluorometer. The distance is really short. It's only 173 meters. This is the restitution curve that we got. So this is injection. So we injected 500 grams of fluorescein or uranin. It has different names. We already see a first arrival 15 hours later. No, not 15 hours, 4 hours later, because we injected at 11, and it came. It arrived at 3:30 in the afternoon, and we see a peak, like more or less 6 days later. We see the peak, and then it goes down. But this is still. My colleague Amael still needs to analyze more deeply this restitution curve, so we don't have all the information yet. I also don't know what the recovery rate is. I asked him earlier today, like, what was the recovery rate for this tracer test? But yeah, the data still have to be analyzed. Of course, we also measure turbidity as well, just to have an idea if there's interference for our data. And temperature we also measure as a standard. So yeah, this is a first tracer test that has been done. I can't tell you that much about it yet because the data still have to be analyzed, but we will do this type of work for each karst system. We know that it's important. We saw in this project that it's quite important to have a much more detailed analysis of nitrates instead of the ones that is done now 4 to 12 times a year. We see with high resolutions that is, for some sites at least, a very high variability linked to rain events. Now we also want to see how this corresponds to the hydrogeology of the karst system after we characterized it with tracer testing. So this is something that is planned for the future, like the effect of this nitrogen variability and maybe also some unknown sources, like why does this nitrogen content doesn't go down despite the fact that this Protecto program is in place. So this is something that we want to find out. And of course, once we have this knowledge, we will provide it to the water producers that can then hopefully put in place some program to limit this nitrate pollution. So this was the project. So this is the project. It's still ongoing. We have a website. It's epukarst.be, but sometimes it takes some time to upload the new data. So, but if you are interested, you can always check out the website. So that was it for me. Thank you. If there are questions, don't hesitate. So there's one question from Luca. She asks if Protecto encourages changes in agriculture when the nitrate level at the abstraction site is too high. So yeah, that's correct. So when the nitrate level is getting too high or close to this limit, Protecto is put in place. And then it can't, unfortunately, it can't put limitations, but it gives recommendations to the agriculture to say like, okay, there is too much nitrogen remaining still in the soil after last year's production agricultural season. Then they recommend like maybe next year you could use less because obviously there is too much remaining. You use too much nitrogen, which is affecting the groundwater. If there is a shallow monitoring network, no. So there's only this Protecto that takes soil samples. Of course, they take the soil samples on the agricultural fields, but there's not some preliminary action or monitoring that's taking place. So it's basically at the catchment sites by the water producers. They say like, okay, the nitrogen content is getting too high, and then Protecto is put in place. They take soil samples. So it's quite some time that goes over between the actual monitoring in the water and then Protecto giving recommendations. Yazeed, you had a question?
Thanks again, Sofie, for a very interesting presentation, and looking forward to some of the results that will come out, because obviously this is still a work in progress. But maybe maybe kind of similar to what Luca was asking about is in terms of the shallow monitoring. You know, particularly with your nitrate concentrations so high in the vadose or the unsaturated zone, and also consistently elevated across the drips, if I'm not mistaken. How do you plan to monitor the nitrate dynamics in the vadose zone itself? So would you maybe look at using lysometers as a starting point, you know, so you kind of capture and quantify what you have there using the lysometers, and then how will you then integrate those measurements with your drip water and even your plant tracer test that you so rightfully point out that you'll be undertaking to understand the transport pathways, as well as the lag times and these seasonal variations. And we know, you know, sometimes the vadose zone, you know, it can act as a buffer as well as a source for nitrate reaching the aquifers. So I just wanted maybe some clarity around how you tend, because I think it would be good if, yeah, you're looking at the soil, but it seems to me that the more important pathway that needs a little bit more quantification, if I can use the word, would seem to be the unsaturated zone. Thanks.
Yeah, so that's a bit of I think limitation of the Epukarst project. Of course, we are limited in budget and in time. So I don't think they will, it's not our part as well. So we are really focusing on the hydrogeological characterization. But they will take soil samples. They will go also deeper, up to 4 meters. But of course, that's still quite limited. And we do the drip systems. I don't think they will do other type of.
Do you know the depth? Do you know the depth? Sorry, do you know the depth of your vadose zone, the unsaturated zone? How deep it is before you get to the water depth?
No, it's really variable. So we did this ERT tests as well. Okay. So we are looking at the depth, or at least the thickness of this soil before you actually get to the limestone karst system. So it can go up to 2-3 meters, and at some points it's deeper. It goes up to 10 meters. So it really depends on the area. So, but that's why we're doing this ERT test as well, to have an idea like, okay, which zones have a deeper layer of ground above we actually get to the karst system. So this is information that we have, but we are limited in what we can provide. What we also want really study is how nitrate itself changes into other chemical compositions, which of course is also something that happens. But I don't think they will look into it in detail there's this other company that is taking the soil samples, so they will look at the samplings, but I don't know how they will analyze it more in detail. That I can't tell. But yeah, there's definitely limitations, unfortunately.
Thanks, Sofie.
So I think that's it. Thank you very much to Yazeed and Romza. Thank you for presenting. Unfortunately, we didn't have that many participants this year. I know that a lot of people also watch it afterwards, especially our followers in the US, because for them it was a bit too early to follow today. But yeah, I will post it online on your YouTube channel. You can revisit it, and of course, I can, if you want, I can share your presentations, and then maybe if there are further questions, I can forward them to you, or you can ask directly to the presenters. There's someone is still writing something. I think, Adrian, do you still have a question, or? No, he stopped typing, so I think that was it. Oh, no, okay. Okay, well, thank you very much. And we're looking forward to the continuation of this of your research, Yazeed, the next by your colleague at least. And yeah, I will keep a closer eye to what's happening in Indonesia, which apparently has a lot of karst, which I was not aware of. So thank you. And have a nice
so
lunch. For me, it's lunch, so I'm looking forward for some lunch.
Same here. Yeah. Thank you, colleagues.
Okay.
Bye-bye.
Bye.